Thank you. So this is a new talk, so I'll try to keep it to time and try to keep it more or less coherent. So let's give it a shot. The title of the talk really is it doesn't really clarify that there's a lot of aspects of consistency in our system that we tend to ignore or overlook. So that's what we're going to be talking about. Just a quick note here, I'm not trying to offer any solutions, just trying to expose problems in a way that may be a little bit foreign to some of us, and hopefully will help us reason about our systems. Just from a synoptic standpoint, what I'm looking to cover here is our systems exist in the physical world. We're trying to deal with that. That's what we're trying to model. We don't want to annoy humans. They get irritated under certain circumstances. Our systems are global, whether we like it or not. We're trying to maintain availability and uptime. And we'll cover some slightly mind-bendy conceptual models and review a modern system. So, what are we trying to achieve? We basically, in any of our systems, are looking to create a model of reality. Whether it's, in the case of my company, we work on warehousing software. So we're trying to model orders and items, and we're trying to perform certain computations and then create certain business decisions as a result of those things. This applies to all of our software for every single one of us. That's really the nature of the problem we're trying to solve in one way or another. Model reality, perform computations, and hopefully profit. So in the course of this, humans have a lot of interesting expectations. Is it up? Is it fast? Is it behaving in the way that I expect? It should be expedient. It should be consistent. And so this really feeds into the consistency model. So when we're talking about consistency models, this actually has a pretty good technical definition, which this is Kyle Kingsbury's definition: a set of all histories of operations allowable under a system. And the way I like to think about it is it's really a contract between the system and the user, or the system and the programmer, or whomever the various parties are. This is a sort of a contract. What are we agreeing to? What are we offering in terms of our guarantees? What can I hang my hat on? And so there's some common consistency models here. So linearizable consistency is one that whether you are aware of it or not, you're probably pretty familiar with it. And it's basically the notion that all operations have to complete in a certain order. It's essentially a single file line. When we're talking about reads and writes in a database, we're saying that I want all of my reads and writes to interleave in a very specific order, and I want the operations to complete. I want the previous operation to complete before the next operation is initiated. And then there's serializable consistency, which is very similar, with the caveat that essentially we can have certain people in that single file line. We can have them cut in line so long as they don't interfere with each other. So long as they don't take the thing that the person behind them in line is looking to have. Sequential consistency, fairly similar to the above two, except insofar as the operations can initiate in any order, but they can be only applied in a very specific order, and everyone has to agree on the order that they're applied in. A good example of this would be a queue, whether it's RabbitMQ or something like that. You can put the things into the queue in whatever order you want, and there's no guarantee about what order they go into the queue, but there is a very specific order at which they're processed out of the queue. So this is something that you probably have in your systems. One interesting consistency model, which is starting to become more popular, is causal consistency. There's, I believe it's REAC and a few other databases use this. And basically, a causal consistency model means that you can apply operations in any order, so long as you record your precursors, and you can view outcomes in any order, so long as you consider the precursors of the operation that you're observing. Eventual consistency basically offers almost no guarantees. You're just saying that the operation will complete someday, and if the system comes to a rest, that everyone will see the same view. So these systems tend not to come to a rest. They tend to keep going, and it's kind of a moving curtain over the course of your operations. But in theory, if your operations quiesce, then they will all be applied in a way that's consistent, and all participants in the system will see the same view. And then there's pram and read your writes and repeatable read and monotonic write and monotonic read and write follows reads. There's quite a lot of different consistency models that I won't get into here, but they all vary in some subtly different way. And so I like to think of linearizable consistency being one of the most common ones as kind of like a waiting list, so or like a clipboard at a restaurant. Yeah, you can try to grab the clipboard out of somebody's hand, but generally speaking, only one person is going to be at or holding the clipboard and writing on the clipboard. And if somebody else wants to read it or write on it, they have to take it out of your hand. You have to yield it to them. And so in a sense, that's an exclusive resource. So this allows us to have a clean linearization of the names on the list at the restaurant. You'll see a single zip line is also a linearizable resource. You can put as many people on that zip line as you want, but they will all finish in the same order that they started. Therefore, that's a good metaphor for a linearizable system. Eventual consistency, there we go. Eventual consistency is like a bunch of zip lines, insofar as these zip lines will, you can have a bunch of different people start at the top, and they'll all get to the finish, but they might not get to the finish at the same time. So you may have an inconsistent result for a little while, and eventually it'll be consistent. Then there's a casual consistency or causal consistency, and the metaphor that I like to use for this is a silly one, but one that I think helps kind of congeal the idea for me, and that is when I put a glass on a table, that glass doesn't jump to the other side of the table. It generally doesn't. That when I put it there and then I look away, so long as nobody messes with it, I pick the glass up, it's going to be at the place that I left it. And I don't have to communicate with Ashburn, Virginia in order for it to be there when I look back. It has local coordination-free causal consistency. The system, that is the table and the glass and my hand putting it down, those are precursors to my hand picking the glass back up. It's going to be in the same place that I left it. So this is a causal system. And essentially what this brings us to is reality is a causal system. So the world around us is causal. The reality that we're trying to model is a causal system. So why shouldn't we use causal consistency models in order to consider that in our systems? And the reason is that in a lot of cases, causal consistency models are complex, and they come with trade-offs that we may or may not want. So that's why a lot of our systems, when we're trying to have a global 24/7, 365 system, that they tend to use simplifications of causal consistency, like linearizability, serializability, sequential consistency. These are systems that use a central arbiter in order to enforce a kind of crude causality, so that we can have a result that agrees with our users' expectations, that will allow us to not irritate the user by having the glass jump from one side of the table to the other spontaneously. So in doing that, we also incur some trade-offs that we'll get into in a bit. And so why not use wall clock? when we're looking to have all of the system, all of the parties in the system read whenever they want and write whenever they want, we want to have a system that is available and geo-replicated and so on. So why don't we use wall clock? This is just a simple way to interleave, to provide a specific interleaving of operations. I could use that to order the operations across the entire system. So no, I don't want to do that. I definitely don't want to do that. And the reason is that NTP is unreliable, right? That's the only reason. It's, right? No.
Everyone know what NTP is?
Network Time Protocol. So the other reason is that it turns out simultaneity is not a thing. And if you talk to a physicist, they'll try to break the news to you. Sorry, there's no such thing as simultaneity. That is a much deeper topic. But essentially, time is weird, and it doesn't exist in the way that we think it does. And that if you ask what time it is in Tokyo, the answer is, well, the Universal Time Coordinated Convention says it's this time, but it's actually kind of a more complicated answer than that. And so when you have a globally distributed system and you're trying to compare, or you're trying to create interleavings of operations in a way that is satisfying to users, where the glass doesn't jump from the one side of the table to the other, that it turns out wall clock is a really terrible idea for this. So some advantages and disadvantages of some of these consistency models. So with linearizability, you get strong consistency, and you see this in the literature. That's the term that they use. I think that it's a little bit of a biased term insofar as it's strong in that it gives you a consistent worldview, but it's weak in that you have to have patience. You have to travel to the central arbiter in order to observe the linearization, be it a relational database in many cases or what have you. And there's a single point of view, which is nice because it gives us a simplified sort of way to be conformant with our causal expectation. Serializability, it's almost the same, but with cutting in line, we can have a little bit of concurrency. And we still have to have patience as we travel to the central arbiter, the database, and back. Sequential consistency, pretty much the same, except for the fact that we're limiting how we're applying those operations, not how we're initiating them. Eventual consistency, pretty much no promises when it gets there. And causal, there's no patience required. We can have readers and writers going to their heart's content so long as they're applying their precursor operations. And we can ensure that we have something that's compatible with our causal reality without having a central point of view or a single point of failure. And so what consistency models do we really use in practice? When we're thinking about this, we tend to think about this from the point of view of MySQL or Postgres or Sybase or what have you. So yes, obviously those linearizability and serializability and end story, right? But what's actually going on is a little bit more complicated. That, as you can see, we have a whole host of different consistency models going on in our systems. It's not just the one, it's not just the database. In our system, we have a tendency to view our system as just being the database, or just being the database plus an application server or a microservice or whatever. But the reality is that our system is the whole thing, including, I should say, the users themselves, their causal expectation, the ad hoc consistency model in the web browser, if you're lucky enough to use UDP, you have an atomicity guarantee. With TCP, you're talking about linearizability insofar as that TCP connection guarantees that I'm not going to get a packet out of order. When, if I drop a packet, it's going to wait until it retries that, or until forever, to continue that connection so that I have a clean linearization of packets in a specific order. In theory, many of our web servers and microservices are stateless, but that's actually changing with more modern designs. We have eventual consistency in the case of Elasticsearch, sequential for RabbitMQ and SQS. We have eventual or causal if you're using React. It has both modes. We have our SQL database, Memcache, and so on. And so we're dealing with a whole host of different consistency models. And so it's no surprise that this stuff is confusing. That we're coming at this, we tend to come at this sort of problem-solving exercise from the point of view of I'm dealing with one thing with one consistency model, but in most cases you're actually dealing with 6 or 7 different consistency models all back to back. And so we could have magic castle technology to come to the rescue in the form of Amazon Web Services or GCE or what have you, and make it their problem, right? That's a pretty good solution. And the tricky part is that while AWS is pretty good and it does solve a lot of problems and makes a lot of things easier, we still have to think about consistency models in order to really conceptualize our systems thoroughly and properly and try to avoid the weird behavior that we want to mask from the users as much as possible. And so we've got a couple of examples here of the different consistency models in AWS. Why do we like TCP? We covered this a little bit. Essentially, it gives us a nice clean abstraction where I can say no matter what the network circumstances, I'm going to have a clean linearization of packets going in and coming out, and I can lean on that. I can rely on that. The downside, of course, is that it does have foibles. Similar sort of situation for a serializable RDBMS. It gives us certain guarantees that are nice and inconvenient at a cost of occasionally having problems. It tends to work better on smaller scale. When you need to geo-distribute, RDBMSs tend to fall over in a pretty spectacular way. So why isn't eventual consistency the answer? That seems nice. We can have readers and writers all going to their heart's content, and nobody's waiting for anybody. We can have total availability. That sounds awesome, right? The problem there is that it is incompatible with the user's worldview. They tend to have a causal expectation, and with eventual systems, that glass will jump from the one side of the table to the other. The user will be very distraught about this. And you'll have an angry phone call or what have you. The insidious threat of eventual consistency models is that we generally will create overlay consistency models that we don't think about very much, where we're compensating for whatever the particular quirks of MongoDB or what have you. That we have workarounds that we put in place to try to cope with these. And so just a couple of scenarios to talk about real quick. Li-Fi, whenever you get onto an elevator and your phone cuts out, your Slack starts wigging out and you have to swipe up and restart it. That is because of TCP linearizability gone wrong. We've got, looks like I'm a little short on time, so I'll blaze through these. Whether you like it or not, your system is distributed, and you have to deal with this one way or the other. A lot of people can kind of skate by for a while and not think too hard about it, and eventually you will get bitten by this problem in one way or another. So for my parting words, I really like causality, or I should say causal consistency. It's really very nice when you can use it. Serializability and linearizability have pretty serious limitations, but they're also an entrenched technology that we have to deal with, and so we would best move forward with an understanding of those limitations. Rather than just damning those systems entirely, let's reason about them, understand those limitations, and apply that accordingly. Definitely don't use wall clock for anything ever. So thank you very much.